Lesson 12. This one actually has two essential questions. First, how do I set up factor puzzles for numerical proportion problems? That just means setting up a factor puzzle for a proportion that isn't in a word problem. It's just numbers. And then how can I tell if a problem is a proportion problem? So you may come across a variety of word problems over the course of your, math career or in life, and you have to determine, is this a problem that can be solved with a proportion? Do I want to set up a factor puzzle here? Not every word problem is a proportion problem. So we're going to talk about the attributes of proportion problems. First, let's solve each of these numerical proportions. So these are numerical proportions. There's no word problem involved, but you can see that we have proportions because we have equivalent ratios. The first is the ratio A to 32. So I could write that in the very first row of my factor puzzle. A to 32 is my first ratio, and that is equivalent to 15 to 40. So I can write 15 to 40 in the second row. And then all I need to do is solve my proportion problem. It's that simple. 15 and 40 have 5 in common. 5 times 8 is 40. 4 times 8 is 32. 5 times 3 is 15. And that means the missing number must be 12. A is equal to 12. Let's look at number 4. We have another numerical proportion problem. Our very first ratio is 27 to 45. And our second ratio is 21 to B. Now, if you want, you don't even need to write the variable in your factor puzzle. You could just leave that empty space. We've always had an empty box there before, so feel free to leave that empty box. You just know that B represents the unknown. And we'll solve it. 27 and 45 have 9 in common. 9 times 5 is 45. 9 times 3 is 27. 7 times 3 is 21. And that means the missing number must be 35. Oops, I almost said A. Should be B this time. B is equal to 35. And keep in mind, I'm not just saying the answer is 12 or the answer is 35. I am labeling my variables. I'm telling you A is equal to 12. B is equal to 35. Please get in that habit of labeling your variables. Now let's talk more about proportions. You know proportions are when you have equivalent ratios, right? That means ratios that are equal to each other. And you're assuming that, you have a constant ratio. Something is staying the same, right? That ratio, whatever you're comparing, is staying the same. You may be changing the quantity of the ratio, but it will still be the same as the basic ratio. Think of ratios like recipes. You can make more of a recipe, you can make less of a recipe, but no matter what, the ingredients that you use and the ratio of those ingredients is always going to stay the same. Take a look at this root beer float recipe. This is just an example. What if I said, you and a friend are making root beer floats, so, that's 2 people. So you have a ratio of 4 to 2. 4 cups of root beer to 2 scoops of vanilla ice cream. And that'll give you enough, root beer floats for the both of you. What if you want to enjoy a root beer float by yourself? So now you've got a ratio of 2 cups of root beer to 1 scoop of vanilla ice cream. What if we're talking about 4 people? Maybe you invite 3 friends over for a picnic, so you and your 3 friends, that's 4 people. Now you have 8 cups of root beer to 4 scoops of vanilla ice cream, 8 to 4. All of these ratios are actually the same because you have a constant ratio of the original recipe. The original recipe is not changing, it's constant. And you can prove it by simplifying these. 4 to 2, if you simplify that, you end up with 2 to 1. Take a look at the other ratio, the one with the picnic. Let's see, let's look at 8 to 4. If I were to simplify that, again, 2 to 1. That's because the ratio of root beer to vanilla ice cream is staying the same. It doesn't matter whether you have 2 people over, 3 people over, 10 people over. That ratio of 2 cups of root beer to 1 scoop of vanilla ice cream is staying the same. You're not changing the recipe, you're just making more of it. Now let's apply that idea to some of these problems. You have a couple different problems here presented on, let's see, page 32. And what we're going to do is we're going to circle the number of each problem that is a proportion problem, and then we're going to solve it with a factor puzzle. We're going to circle the basic ratio in each factor puzzle. If a problem is not a proportion problem, we have to explain why. So not every one of these word problems is a proportion problem. If it is, we can solve it. If it's not, we're going to have to explain why it's not a proportion problem. You don't actually have to solve the ones that aren't proportion problems unless you really want to. So let's look at number 10. Let's see. Peachy Paint Company used 20 cans of blue and 15 cans of yellow paint to make grasshopper green paint. They have 8 more cans of blue paint. How many more cans of yellow paint do they need to make more grasshopper green paint? This to me sounds like a proportion problem. And the reason I'm thinking it is a proportion problem is because I'm assuming that they're not changing the ratio of blue to yellow in order to make that grasshopper green paint every single time. Think of it as being a recipe, the recipe of blue to yellow paint in order to make grasshopper green. If I change the ratio of blue to yellow, I might end up with a different shade of green and not the grasshopper green that they're working for. So I'm assuming we have a constant rate. We have a recipe for paint color that we don't want to change. That means I can circle number 10. That means I can solve it with a factor puzzle. I'm going to use labels. Let's see, we have blue to yellow, and we have 20 cans of blue, 15 cans of yellow, and now we've got 8 more cans of blue lying around, and we have to figure out how much yellow paint that is. So I can solve it. Let's see. 20 and 15 have 5 in common. 5 times 4 is 20, 2 times 4 is 8, 3 times 5 is 15, and that means the missing number is 6. So they must need 6 cans of yellow paint. It also said we had to circle the basic ratio. Well, the basic ratio here is 4 to 3. For every 4 cans of blue paint, I need 3 cans of yellow paint. Let's look at number 11. Mr. Talley's art class uses 2 bags of markers each week. Mr. Petro's art class uses 3 bags of markers one week, and then 2 bags the next week, and then continues in this pattern. If Mr. Talley used 14 bags of markers, how many did Mr. Petro use? Well, in order for this to be a proportion problem, I'm going to assume that the ratio of markers being used by Mr. Talley to the markers that Mr. Petro's class is using, I'm assuming that the ratio between the 2 classes is going to be the same. However, it doesn't sound like that's always going to be the same. You know, it looks like the first week, let's see, Mr. Talley uses 2 bags. I'll do T for Talley. And Mr. Petro uses 3 bags. So that's the first week. But then the second week comes around. Well, Mr. Talley still uses 2 bags every week. That hasn't changed. So Mr. Talley's is still the same. It's constant. But Mr. Petro's, on the other hand, well, they use 2 bags the second week. This shows me that I do not have ratios that are constant. I do not see the same equivalent ratios. So I am not going to circle number 11. It's not a proportion problem. And I'm going to explain that the ratio of markers used between the two classes is not constant. So remember, I have to have ratios that are constant. I would have to have a ratio of 2 to 3 every week. It doesn't matter what week. I would always assume that, Mr. Talley's class is going to use 2 bags and Mr. Patriot's class would always use 3, but that's not the case here. Alright, so let's take a look at our takeaways. First, if you want to set up a factor puzzle to solve a numerical proportion, the first ratio always goes, in the first row. The second ratio always goes in the second row. And also, a proportion problem is only, or I should say a problem is only a proportion problem when you have a constant ratio. I can't stress that enough. You have to assume that the ratio between the two quantities is always going to stay the same.